G is a subgroup of Sn, where Sn is the symmetric group of degree n, or n symbols, with n symbols. Okay, so so this is the Cayley's theorem. So it is a very fundamental theorem in the group theory. So now we will make the statement of the generalized Cayley's theorem. So let me let us first consider the action. So let G be a group. Let G be a group. Let G be a group, and H be a subgroup of G. Let G be a group and H be a subgroup of G. Now consider the action. G acts on G mod H. Notice that G mod H is the set of all distinct left cosets of H in G. It is not a group, it is the only set. Okay, so take the action G acts on G mod H by take any G in G and take any element in G mod H. So we can action is nothing but G xh for every G in G and xh in G mod H. So so you should check that it is an action on of G on G mod H. So therefore, so this implies that there exists a group homomorphism, call that phi homomorphism, call that phi of H from G to S of G mod H, right? So it is the symmetric group of X, right? So it is the symmetric group of G mod H. Okay, now this implies if and only if that phi of G equal identity map on G mod H. This if and only if that phi G acting on any XH equal to T on G mod H acting on XH. So it is equal to nothing but G XH, and it is equal to XH for every X in G. And therefore, if and only if a G inverse XG belongs to H, so it is of H equal to, sorry, is equal to X inverse G. So that means that X inverse G X of H equal to H for every X in G, and uh, and this implies that G belongs to XH X inverse for every X in G. Thus, it is if and only if G belongs to the intersection X in G XH X inverse. So therefore, kernel of the map phi H is equal to the intersection of all X in G XH X inverse. Okay. And notice that it is a normal subgroup of G. It is a normal subgroup of G, and also that this kernel of phi H, it is contained in H, right? It is contained in H. Okay. Now, if you take let K be any normal subgroup of G, such that K is contained H. This implies that XK X inverse is contained in XH X inverse for every X in G. So and it is equal to K, right? So this implies that K is contained in XH X inverse for every X in G, and that implies that K is contained in intersection of X belongs to G XH X inverse, which is equal to our the kernel of phi of H, right? So we have proved that the kernel of kernel of pH is the largest normal subgroup of G contained in H. Contained in H. Okay. And it is in fact the statement of the generalized Cayley's theorem. So let me state this. So generalized this from so G let G be a group, and then consider the action G acts on G mod H. So okay, so this is of G. Then then there exists a group homomorphism group homomorphism phi of h from G to the symmetric group of G mod H such that kernel of phi of h is nothing but intersection of x h x inverse and x in G, and the kernel of phi h is the largest normal subgroup of G contained in H. So it is the it is a statement of the generalized Cayley's theorem. So remark in particular, if you take if H is equal to identity, then phi of H equal to phi. So where phi is the homomorphism from G to SG. Okay, so when it's a phi, so then if it's equal to 1, then it is the Cayley's theorem. Okay, so it's equal to just E. Find it. So okay. So now let me give some application of this generalized Cayley's theorem. So the first application is application of this theorem. Application is, you can check that the application, that is the number one, that sorry. So let G be a finite group. Let G be a finite group, and H is a proper subgroup of G such that order of G does not divide index of H in G factorial. Okay. G is then is not simple. Okay. So how one prove this? So it is the it is just the application of the Cayley's theorem. So consider group homomorphism phi of h from G to S of G mod H, and and kernel of pH is equal to that the intersection of x belongs to G, x is x inverse. So it is, and it is by the Cayley's theorem. Okay. Okay. Now, if now now by the first isomorphism theorem, G modulo kernel of pH, it is isomorphic to a subgroup of, that is, it is phi of G, it is a subgroup of S of G mod H, right? So this means that order of G modulo the kernel of pH, it divides the index of H in G factorial. Sorry, it divides the order of S of G mod H, and which is equal to the index of H in G whose and factorial. So, and since order of G does not divide this, so since order of G does not divide index of H in G factorial, this implies that kernel of H is greater than 1. That means that kernel of pH is non-trivial, and also it is the and also it is the normal in G. So we have a we have a non-trivial proper, and also since kernel of phi of H is contained in H, and H is also and H is properly contained in G, so we have a proper non-trivial normal subgroup of G. So this implies that G is not simple. Okay. So it is the very important result to take that with on. For example, since 5 divides order of G, implies that there exists a subgroup H of G such that order of H is 5 by Sylow's theorem, right? and then and compute the index of h in G. So what is the index of h in G? It is nothing but order of h by, sorry, order of G by order of h, and which is 3. And since and now order of G, which is 15, it does not divide 3, which is equal to, sorry, it does not divide 6, which is equal to the index of h in G is factorial. This means that, implies that G is not simple. So any group of order order 15 is not simple, and you can check uh, for groups of order 12, 21, anything. Okay. Okay. So okay, so it's over now. Now we have now I give now I give one more applications of the Cayley's theorem. So let me state this first. So let G be a finite group and H is a subgroup of G, and G mod and let G index of H in G is P prime, and P is the smallest prime if if this is P, where P is a prime, and and P is the smallest prime dividing order of G, then H is normal in G. Okay. So it is also a powerful result. So we see this result for a special case. So if p equal to 2, then index of h in G is 2. Then we all know that h is normal in G, and 2 is the smallest prime dividing the order of G, right? So it is the generalization of that. Okay. So let me prove this, that if H is a subgroup of G and index of H in G is P, and P is the smallest prime dividing order of G, then H is normal in G. Okay. So proof. So yeah. So using Cayley's theorem, using generalized Cayley's theorem, if you want, generalized Cayley's theorem, we have a group homomorphism phi h uh, from um, it's a G2 S of G mod H, which is equivalent to here SP, uh, since index of H in G is P. So this is equal to SP. Okay, and kernel of phi of H is it is the normal subgroup of G, and it is also contained in H, and it is the largest normal subgroup of G which is contained in H. Okay. Okay. Now, if I if we want to prove that H is normal in G, so suppose uh, suppose you have shown that H is normal in G, then obviously that H is the largest normal in G which is contained in H. So our claim is that that kernel of phi of H is equal to H. Okay. So for that 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 is it is enough to show that this index of this kernel of phi of H, which is equal to 1, right? Okay. Now let me first compute that order of so order of G, what kernel of phi of H. This divides uh, order of S of P by first isomorphism theorem. We have seen this. So it is P factorial, and also, and since order of G equal to this kernel of phi H into order of the kernel of phi H, so so this implies that uh, this group also divides order of G, right? So we have this that this divides factorial. So this divides factorial P, and also the same thing divides order of G. Okay. So let me write this again. So this is phi H. It divides order of SP, which is P factorial, that is P into P minus 1 into 1. Okay. So so if So if mm, so let q be a prime which is less than p, and q divides order of g this, then this should implies that q divides also order of g, uh, since this divides order of g and q divides this, so q divides order of g, so which is a contra which is a contradiction, since q is a prime which is strictly less than p, and p is the smallest prime dividing the order of g. So this implies that the only prime which divide order of g's kernel of ph is 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 p, right? So this implies that this is equal to, yeah, so this is equal to p, right? So now g now g index kernel of ph, it is equal to p, and which is also equal to index of h in g, and from here say that h index of this in h is equal to 1. So and this implies that kernel of p of h is equal to h. So uh, and this implies that h is normal in g. So proved, and hence proved. So so we have proved that if index of h in g is p, uh, a prime, and p is the smallest prime dividing the order of g, then h is normal in g. So okay, so it is the so it is the application of the generalized Cayley's theorem. So okay, so let me finish with this. So okay, thank you, it's over.
Thank you, Sabya. Anyone has any question, then they can ask from the audience. Okay, then I think no one has any question. So on the behalf of Mathematical Thoughts team and all the audience, I would like to thank our speaker for giving us his precious time, and I hope he will be available to us in future programs also. So once again, thank you, Sabya, for
Okay.
providing
Welcome.
the very important talk on group action and its application. And I would also like to thank the audience uh, for participating in this lecture series. So thank you all on the behalf of my team, Mathematical Thoughts. Thank you all.
Okay, and I also want to say thanks, special thanks to Sabyasachi for giving time, and he came back from home to campus, and he just I say once, and he agrees to give lectures on this topic. So thank you, Sabyasachi, for your time and lectures. Thank you.
Okay. Thank you.
Sir, one second.
Yes,
Can you
ma'am.
share this document on group? I mean, on Telegram or WhatsApp group?
Yes, yes, we will share it in next 2 3 days. We will share all 5 lecture notes that will be
Oh,
presented here.
okay, okay. Thank you so much, sir.
Okay.
Thank you for that.
Okay.
Okay, thank you all.